Okay, I actually didn't look up, but I think it was Mira asked if we could look at number 4. All right. The best evidence, remember there is your last homework assignment due today. The best evidence for a black hole at the center of the galaxy comes from the application of Kepler's third law. What's Kepler's third law?
It's A cubed over P squared.
I think it goes like this if you're using years, astronomical units, and solar masses. I think that's right. It could be the other way around, but I think that's right. Okay. Suppose a star at a distance of 20 light hours from the center of the galaxy has an orbital speed of 6,200 kilometers per second. How much mass must be located inside its orbit? Okay, so we're going to have to get this equation straight if we're going to do it right. So we look, and I don't have the equation sheet here with us. Does anyone have the equation sheet from a previous exam? Nope. Okay, so let's go back to the website for Moodle, and let's just look at an old exam, because we got the equation sheet with the old exam. Come on. Shh. Call declined. Now it's quiet. I don't get that many phone calls, just for the record. So just go to exam 3. And I didn't upload exam 3. Then let's go to exam 2. What do you say? Got to have my equation sheet. There we go. Sure, save it. I don't care. Oh, no. It doesn't have the equation sheet on this. It's just the questions. What was that? From previous year?
Mm-hmm.
Yeah, it's a good call.
Might have it.
Okay, the student copy has to have the equation sheet. Next step, if it didn't, would be what you said.
Yeah.
But the student copy has to have the equation sheet because I give you equation sheet. So Kepler's laws, we have...
First page.
Yeah, it's here somewhere. There, that one. So it's a cubed over p squared equals m. So I put it upside down. Right, there's 2 versions of it here. Well, you can't see. There, fixed it. So now we have to find the period. The period is the time for one orbit. We know its speed and we know its radius. So we have something going in a circle. We know its speed and radius. Yes, we can say, well, the circumference is equal to the distance it travels in t equals the period. And so that means that distance is equal to v times the time, which is the period. So the period is going to be the distance over the speed, which would be 2 pi radius over the speed. So period is that. And then we need the semi-major axis, that is the radius. So mass is equal to a cubed over p squared is equal to r cubed over parentheses 2 pi r over v quantity squared. is equal to, and I'm going to write this out in long form just to make life easier for us. Remember, when you divide fractions, it's invert and multiply. R cubed, two of those cancel with the R squared, and I end up with the mass is R times speed squared over 4 pi squared. Now you just put in the numbers. I'm not going to put in the numbers. I want to take away all the fun. But now you just put in the numbers there. And this is going to give you the mass in solar masses. Remember, the units were, if I use years for the time, so we have to pay attention to the units there. I need my time in years in my answer, not in seconds. And if we use astronomical units for the radius, so we need to convert that radius into astronomical units. So you've got some unit conversions that are going to be really fun.
So we're going to have to convert the astronomical unit. We're going to have to convert it to years.
Where we're going to have to convert time and year into years, yes. And distances into astronomical units.
So for velocity, what would need to be the units for that? Would it still be the...
Well, let's look at what units do they give us in the problem.
Light hours.
Is that the homework question?
Yeah. So they gave us speed in units of kilometers per second, and they gave us R in light hours. So that's the speed of light multiplied by 1 hour. So we're going to have to take those, and when we do all of our work, we're going to have to convert our units so that the speed will be in, instead of kilometers per second, well, yeah, you could just convert all of the distances initially into astronomical units, or instead, you could wait until the end of the calculation, pay attention to what your units are, and then do the conversion.
So we don't keep it at meters per second. We do it, we change it to...
Well, we need to, in the end, have, instead of meters, astronomical units.
Oh.
And instead of seconds, years. So when you do that calculation, your units are going to be, right, if you just look at this, distance times distance distance squared over second squared, and we're going to have to, so we're going to have distance cubed over time squared, and then we're going to have to convert those units.
So then for light hours, it would just change hours to years?
We're going to need to convert the units. It's not just changing hours to years, because you still have the speed of light in there.
Yeah.
So the unit conversion is really the most difficult part of this. There is another version of the equation that actually has the numbers, and I don't think I have in my equation sheet the version that actually has all of the constants. I'm trying to contemplate if it's quicker to do it from the beginning or to look it up. This is the fundamental of the equation. And so if you solve this, you have the mass is v squared r over g. And this is then in standard units. You could find, the speed in meters per second, the radius in meters, and use the standard g, and that would give you the mass in kilograms if you want to do it that way. And since v we determined was, well, actually v was given to us and r was given to us, there's no conversions.
So you
Well, you have c squared times hours squared. So I'm going to put 3600 seconds squared, right? So because actually, I better look more carefully. What did it give us the speed as? No, the speed was kilometers per second. My mistake. $66,200 kilometers per second. And R is 20 light hours. So that's 20 times the speed of light times 3,600 seconds. And so if I put those numbers in, I'll have, there I converted that to meters per second. Times. I always write this way. So now it's all in standard units. You put in those numbers and you'll get your answer in kilograms. But I think it asks for it in solar masses, doesn't it? So you need to take that answer and divide it by the mass of the sun to get it in solar masses.
It just says how much mass.
Oh, okay. So it just says mass. You can do like that and just get in kilograms. Okay, so that was a pretty good problem, huh? By the way, when you're doing your solutions, make sure that you do your solutions. This last time when I was grading, there were some answers that were pretty much verbatim from the solutions that the textbook gives. That would be a sign of cheating. Make sure you're not cheating on your homework, okay? Any other questions on the homework? Alex says no.
I have a question on 7.
7?
Yeah.
Suppose the stars in an elliptical galaxy are formed within a few million years shortly after the universe began. So that means they're over 13 billion years old. Suppose these stars have a range of masses, just as the stars in our own galaxy do. How would the color of the elliptical change over the next several billion years? How would this luminance change? Why? So we start off, and this kind of relates to a question we had in the last homework assignment about the, what evidence can you give that stars are being formed still presently in our galaxy? We have stars of different mass. What can you tell me about stars of high mass? There should be 2 important things you can name about them. They're related.
Their lifespan's pretty short.
Lifespans are pretty short. So only in the early stages of this elliptical galaxy are we going to see those high mass stars. Then the second thing is, what about the light they give off? It's what? It's brighter and it's hotter, which makes its color bluer. So in the early stages, because massive stars give off a lot more light than low mass stars, we're going to see primarily the light from these massive stars when it's young. So we're going to see it as very bright and blue. But after these stars die, because they have short lifetimes, what are we left with? The low mass stars. And what are the low mass stars color? Red, and their luminosity is lower. So we're going to have less light and it's going to look red. So we have that progression because of the life lengths, the lifetimes of stars with different mass. Understand, Juliet?
So pretty much, what we say for the question would be just that over the next billion years, we would see more stars that are less massive, lower luminosity, and then they'd be more likely to become red.
Well,
Or,
start off with what's it going to look like in the early days, in the first 10 million
So with the
years.
blue
What's it gonna look
stars
like?
and the massive ones with the
Okay,
high
so
luminosity.
you're going to see bright blue because you have massive stars giving off a lot of light that's blue. And then when those stars die, the color, the brightness is going to dim, and the color is going to shift from being blue to shift to being red, because all you're left with is the long-lived stars that are low mass, that give off less light, and have the different color, the reddish color. All right, let's do some reviewing to get ready for the final exam. So I looked it up, chapters 129, yeah, that's right. The final exam will be over chapters 1 through 29. It's cumulative over the entire semester. Seeing what we've learned. What have we learned about? We've learned about a lot. It's always surprising when you get to the end of the semester to think about all of the different things we've learned about. And so I'm going to briefly review those things. The exam is December 10 at 3:30 p.m. right here. So now the parts here broken down don't match our textbook. I wrote this review for a different textbook. I figure I covered the same stuff, so I'm going to go with the same review rather than writing a different one for the different textbook. But the first thing is always true. There's going to be a repeat of the scientific method question. You've already had the scientific method question once. What did you have to do for that scientific method question? Well, first, before you do that, you have to regurgitate these steps.
Yes.
So make sure you know these steps, right? Because you're going to have to write those down. That's half of your credit for that problem, is having these steps correctly written down. And then I'm going to give you an observation. Now we can go to what Leslie was saying. I give you the observation and I say, step 1. I give big blank. And what do you write in step 1? You don't write see above. You succinctly write in short what it said in the observation. Right? I mean, you could write the whole thing in long. It's just going to take more time. That's why I suggest being succinct. Then, for step 2, what are you going to do? You're going to write down your hypothesis. You're not going to say, right, you've already said in the first half, I need to write a hypothesis that's based on scientific ideas that explains why the observation occurred and makes testable predictions. Now you're actually writing a hypothesis that you think covers those bases. Then step 3, you're writing out a test. Really important to me. Your test cannot be repeat my observation. We already know the outcome of that. We need to test a prediction of your hypothesis, not just check and see if what you measured was actually correct. So it needs to be something different than just repeating the observation. And then for the last step, you say, if this outcome occurs, then my hypothesis is confirmed, but I would need to go back and test again in another way. You don't say what your second test would be. You just say, I'd have to test again in another way. And then you say, if I get this outcome, then my hypothesis has been disproven. And so I will need to go back and modify my hypothesis. You don't have to come up with a modification of the hypothesis. Just say, I would have to modify the hypothesis. This is super important to me, right? It's one of the most important things I think students can get out of this class is understanding what science is. We have the scientific method to define how we get information in science. Any questions about this scientific method question? None? All right, moving on. So we start talking about the sky. Now, obviously we have the lab finals separate, but there are things about the sky that you still will have to know, like how do we measure positions in the sky? Use this thing, right? We have the declination, which is the angle north or south of the equator, the celestial equator. We have the right ascension, which is the distance east and west from the equinoctial calor. And so we have essentially the same as latitude and longitude, but it's declination and right ascension. And you should know things like what the equinoctial calor is, where we measure zero right ascension from, and what the celestial equator is, the celestial North Pole, the horizon, the zenith, the nadir. I should know what these terms are. Units and distance. You should know what a light year is. Simple definition is the distance light travels in a year. You should know what an astronomical unit is. Average distance between the Earth and the Sun. You should know what a parsec is. A parsec is the distance from the center to, well, it's actually one astronomical unit for the baseline used, then it gives you the distance if you have a parallax angle of 1 arc second. And so there's a direct conversion from a parsec to a light year, 3.26 or something like that. You should be able to calculate a distance if you get a parallax angle. The distance from a parallax angle is real simple, by the way. On the last test, I think there were people that had some confusion on this. The distance is equal to 1 over the parallax angle if you measure the parallax angle in arc seconds. Remember, parsec, parallax, arc second. Here's that parallax angle. There's the distance of 1 AU. And this is the distance. Actually, that would have worked. That's the distance we're determining. And so the distance in parsecs is 1 divided by the parallax angle in parsecs. So you should understand those different distance designations. Quickly, what is the definition of a day? Day is the time it takes for the Earth to do one rotation. There are 2 different types of days, the sidereal day and the solar day. What's the difference in sidereal versus solar?
Sidereal, the 365 point whatever.
No, 360. Sidereal, the sidereal day is one rotation from the perspective of the stars. That's what sidereal means. So that's 360 degrees rotation. The solar day is from, let's go with noon to noon. So when the sun is on your meridian to when the sun is on your meridian, that's a solar day. Remember, your meridian is the line that goes from the north celestial pole through your zenith to the south celestial pole. What about a month? How do we define a month? Yeah. Based on the lunar month, but the month is not exactly a lunar month. The month has its name month because it comes from the moon. The month, we have 2 periods. We have the synodic period and the sidereal period. The sidereal period is the time for the moon to do one orbit around the Earth. And the synodic is for it to go from new moon to new moon. Why is the sidereal day different than the solar day, and why is the sidereal month different than the synodic month?
The rotation.
Because the Earth is going around the sun, and so the time between noon and noon is going to require just a little bit more than one rotation. And the time between full moon and full moon is going to require, gotta get this straight now. Sure. Yeah, more than one orbit. It's 1.0 something orbits, but it's more than one. So that's why they're different. Lunar cycles. What is the first part? Where do we start the lunar cycles? On which phase? New moon. New moon is the first phase. And then as you go through, just name the phases. Go for it. New moon, then waxing what? Waxing crescent. Then
Gibbons.
No.
between,
That's cool.
okay, there's a half, but what do we call that? We call it the first quarter.
Oh.
First quarter because it's 1/4 of the way through the cycle. It's not a quarter moon, it's a half moon, but it's a quarter way through the cycle. Then comes the waxing gibbous. Then comes full moon. Nobody calls it second quarter, but I suppose you could. What comes after the full moon? Waning gibbous, then third quarter. Finally,
Waning crest.
waning crescent. Now, how do you know? Just you go out at sunset and you look at the moon, and you say, is that a waxing or waning
Is
moon?
that dog? Good terminology.
Okay, dog works. You look at the curvature. If you see a full hemisphere on the right-hand side, like you do on a capital D, then it's waxing. If you see a full hemisphere on the left-hand side, like you do on a capital G, then it's waning. But I said you go out at sunset. If you can see it at sunset, waxing. If you can see it at sunrise, it's waning. What makes the phases for the moon? Okay? It's based on the geometry between the sun, earth, and moon. He said the angle that sunlight's hitting it, that's it. So you have a full moon when we have opposition between the sun and the moon. They're in opposite directions. We have a new moon when we have a conjunction. And of course, the quarters are when it's quadrature. I think I got those right. What's a constellation? It's an area in the sky. Part of the sky, yes. It's an area. It's an area that's defined, within which we have traditional pictograms, but the area is the actual constellation. Now, we have those traditional pictograms. How many constellations are in the sky? 88. Approximately, you don't have to nail it on the head. How many of those are ancient constellations? 48.
Oh, okay.
We have 48, I believe, that are traditional constellations. Whose tradition? Oh, Catholic, okay. I said Catholic. I really should have a hearing check more. They're traditional constellations named by, say, Western scientists. We have the Arabics, the Greeks, the Romans. Those are the groups that came up with these constellations. They're not the only ones. There's, the Chinese have their constellations. The American Indians have their constellations. Different cultures have their constellations. But the ones we use in astronomy come from how our current line of knowledge developed. And so that's where we have things like, Scorpius and Ursa Major, Ursa Minor, and so on. Then there's additional 40. Most of those 40 are in the southern hemisphere. Why would they mostly be in the southern hemisphere? It's not a hard question if you think about it. Where do people live? In the northern hemisphere. Where are all the cultures that I named? In the northern hemisphere. So I think it's like 10% of the world's population is in the southern hemisphere. It's not many people that live in the southern hemisphere. And our traditions in science come from northern hemisphere. So the constellations they saw and talked about are things they saw. And so we have constellations largely in the southern hemisphere that are things like microscopium and triangulum and kind of random made up things that generally don't make good pictures at all. Okay, so what about asterisms? What's the difference between constellation and asterism?
Pattern starts with the constellation.
Not necessarily within, right? Like
Oh yeah, it can be.
the summer triangle is going through bright stars of 3 different constellations. So asterisms are not formally defined star pictures. Constellations do have a formally defined star picture. Asterisms is not formally defined, so you have things like Orion's belt or the Hyades. Those are asterisms. All right, probing matter and light. Moving into the way we observe. Astronomy is largely observational. What can we learn about distant stars? Only what we can receive through telescopes. So we had to learn about telescopes. We learned about the different wavelengths that we can use for telescopes, visible telescopes, infrared telescopes, X-ray telescopes. What kind of telescope makes us happiest?
What are you talking about?
Well, the answer I'm looking for is visible light. We can see it, we're like, ooh, it makes sense to us. But we can use false colors and get a lot of information for different types of telescopes. For instance, you can see where clouds of cool hydrogen gas are if you use a radio telescope. That's really useful because we've learned that stars form where you have cool molecular clouds, which you couldn't see any other way. So different telescopes give us different kinds of information. Now we have up here some other things, some physics terms. This is where we have physics. We have inertia. Inertia is the propensity of an object to just keep going in constant direction at constant speed. Everything has inertia. So if it was left to itself, the sun would just travel a straight line and it would make a beeline out of the Milky Way galaxy. Why doesn't the sun actually do that if that's what its natural propensity would be? It's bound by gravity. Gravity is pulling it into a circle, and then the Kepler's law calculation that we just did can be used to determine how much mass is between the sun and the center of the Milky Way galaxy. And if you do that calculation, you find there's more mass than we can discover. What do we call that missing mass? Dark matter. Okay? We have forces, anything that pushes or pulls. Acceleration, the change in velocity. That would be either a change in speed or a change in direction of motion. So if I have the sun going around the galactic center, it's constantly accelerating because it's constantly changing direction. Kepler's laws pay special attention. We just use one of Kepler's laws. When Kepler discovered his laws, they were simpler because there wasn't the theoretical backing for them. They were just his discoveries. So the first law, orbits are elliptical, not circles, but ellipses, elongated circles, with the sun at one of the focal points. Remember, we had the whole Copernican view that said that the Earth was doing circles around the sun. That's similar but not the same. What was believed before the Copernican view came into vogue? That everything was orbiting around the Earth, including the sun, orbiting around the Earth. And so that was Aristotle's model. Ptolemy modified so you have those little epicycles. The deferent was the big circle and the epicycles were the small ones. And it roughly explained the positions of the planets. And so people believed it for about 2,000 years. And then finally, Copernicus came up with a reinvention of an idea that existed well before the time of Christ, that the sun was the center of our solar system rather than the Earth. And people didn't really accept it because it didn't make any better predictions for the positions of the planets than Ptolemaic system. But Kepler, with his ellipses, Boom! Dead on predictions. You can't argue with dead on predictions, and people accepted, yep, we're orbiting around the sun after all. So that was the first law. Second law, the easy answer is that planets go faster when they're closer to the sun, slower when they're farther away. You know, if you went with the Copernican or the Ptolemaic model, you had constant speeds. But now we have varying speeds. The actual wording says that the area of the line going from the sun to the planet that's swept out per unit time is always the same. So if something's close, it's got to go a big angle. If something's far, it goes a small angle to sweep out the same area. Why did Ptolemy put in his epicycles, the little circles on the big circle? Why did he put those in? Do what?
Yeah, the parallax, they were planets crossing each, like objects crossing each other. Not like, it looked like it has to go back.
Okay, it's what you just said.
I don't want terminology.
It's called retrograde motion. When you watch the planets' positions versus the stars, most nights they move east. But then there'll be a period where they move west, and then they go east again. And so the normal eastward motion is called prograde, normal. And then the motion to the west is retrograde, it's going backward. And so he came up with those epicycles to explain the retrograde motion. Well, we did a lab. You remember the lab where we drew the circles and we traced what direction you have to look to see a planet. And we saw that when the planets are either in a conjunction or in opposition, we're going to have retrograde motion as a natural outcome. And the third law we've just worked on, so I'm not going to review the third law yet.
Retrograde is that thing where, from what I remember, they're moving a certain way, but then around a certain period, they're moving the opposite.
Yeah, as viewed from Earth, the planets generally appear to move east from night to night compared to the stars. But then you'll have a period for maybe a month or two where they start to appear to move west, and then they'll go back to moving east again. All right. Gravitational force, GM1 M2 over R squared. You should know that. Angular momentum, an important one. We've gone through the whole of astronomy now, and you've seen how angular momentum is actually important. Think of something like a pulsar. Why does a pulsar have blips of light that occur approximately 100 times to 1,000 times a second? What's the pulsar doing? It's spinning really fast. Its magnetic fields are causing synchrotron radiation. And what did you say, Alex?
Because it's so densely packed and spinning really fast, and it's got those jets that show.
Right. You started with it spinning relatively slowly. You know, maybe doing a rotation every, like the sun, roughly 20 to 25 days. But then as the mass falls in, for angular momentum to be conserved, there's nothing causing a torque on these babies, so angular momentum will be conserved. And so for angular momentum to be conserved when it falls in, just like a figure skater pulling his or her arms in, the rotation rate picks up. And so the pulsar is spinning so rapidly because of conservation of angular momentum. So you can see how that's important. The conservation of angular momentum, it plays into a lot of things. But that's going to be our most important one. Temperature. What's the unit of temperature we use in astronomy? Kelvins. So make sure that you're comfortable with Kelvin temperatures. One of my students in physics wrote in her scrapbook thing about growing up with parents from a different country, and when they talked about the weather in their home country, they talked about Celsius. When they talked about the weather in the United States, they talked about Fahrenheit. And so this student has a very fluid understanding of both because all of the student's life, they've had both of them in their life. Make sure you understand the differences. Kelvin, absolute 0, 0. What does temperature mean? It's a measurement of the average kinetic energy. It's telling us about how fast the molecules are moving. So at a really low temperature, homework problem from the last assignment, the molecules are going to be moving really slowly, which results in them having a low pressure, which means that gravity can compact them pretty easily. Hence, stars can form there pretty easily. Whereas a high temperature region, they're moving quickly to have higher pressure. It's going to be harder to pack, harder for gravity to start winning. Components of an atom. This one here is, I always think of as trivial because, at least I learned it in high school. An atom has a nucleus, and in the nucleus you have protons and neutrons. It has electrons in a cloud around it. The electrons aren't doing circles. We don't know what they are doing. We can just calculate where they're likely to be found. We identify an element, hydrogen for instance, by how many protons they have in the nucleus. So anything that has one proton in the nucleus is hydrogen. Jumping to a question you had to differentiate between a brown dwarf and a planet and a star. What was the difference between the brown dwarf and a star?
Instead of H1 combustion, deuterium.
Yeah, you have deuterium fusion occurring in a brown dwarf. Deuterium, what's that? Deuterium is hydrogen 2. It's still hydrogen, but it's hydrogen 2. And so that was the distinction between the brown dwarf and the star. Hydrogen 2 fusion versus hydrogen 1 fusion. And of course, a planet has no fusion. Yeah.
I feel like we should be professor. If you have H, isn't that, because hydrogen's already diatomic. I'm trying to remember the difference between.
Remember, there were two H2s.
I know. Oh, yeah. Okay, never mind. Got it.
One H2 is hydrogen. Well, actually, there's three H2s. Because the one I was naming was neither of those. H2 is hydrogen with two things in the nucleus, the way I was saying, which is deuterium. H2 with Roman numerals is a hydrogen atom that has had an electron removed, singly ionized. And then H2 with a subscript 2 is a hydrogen molecule.
There we go.
So our problem only had two, but there's actually three things you can say for H2. H-2, H subscript 2, and H dash Roman numeral 2. You're not going to have a question like that on the test, okay? Don't freak out about that. But we identify the elements by how many hydrogens how many protons are in the nucleus. So helium has 2 protons. Typical helium has 2 neutrons as well. So there's a total of 4 things in the nucleus. It's helium-4. Helium-3 still has to have how many protons in the nucleus? If it's helium, it has 2. If it's helium-3, then it has 3 things in the nucleus, so it has how many neutrons? 1, right? And so you go on in the whole, I don't know how carefully I covered this, I may not have. In the nucleosynthesis process, that is, creator elements we have in the periodic table, hydrogen, you take a hydrogen, you add a proton to it, you have a particle conversion, you have deuterium. You take that deuterium, you add a proton to it, and you're going to have a helium-3. Then you have 2 helium-3s, and you make a helium-4 and 2 hydrogens. That's the typical proton-proton chain that's going on in the sun. Generally speaking, we talk about just adding 1 proton at a time. But if you take helium-4 and you add 1 proton, you know what you get? Nothing. You get no stable element. There's no stable element with 5 things in the nucleus. And so, in the process of nucleosynthesis, it basically stops after helium. Because you can't just add another proton to a helium. Hence, if you look at the gases in the universe, you have roughly 92% of atoms are hydrogen atoms, and roughly 8% of atoms are helium atoms, and roughly none of the atoms are anything else. You have to go to 10 to the minus this much of the others. But you do get some lithium and beryllium because you can have like a hydrogen 2, a deuterium hit a helium-4 or other such things. So you can get past there. But there's another stopper at 8. So you have a stopper at 5, which basically stops you go down a couple orders of magnitude in how common they are. And then you go to 8, you're going to drop another couple orders of magnitude. So virtually nothing during and after the Big Bang larger than 8 things in the nucleus could have been made. That's our understanding of nucleosynthesis. So where do we get these elements like you and I are made out of? It's been a rough day.
Supernovae and exploded again.
Okay, supernovae are the only place where we are going to create in any sort of reasonable number things larger than iron. We can create up to iron in massive stars during their death stages where we're fusing higher elements. Now our sun's right now fusing hydrogen into helium at a temperature of millions of degrees, right? Roughly 15 million degrees, the core. What's going to happen in our sun when it runs low on hydrogen in the core? I'm not on that sequence anymore. I'm just staying with the topic of the elements and how it plays into astronomy.
Wait, after it runs out or when it's really low?
When the core runs low.
Just that little flash.
Before it starts fusing helium, the core is going to slow down, right? Right now we have the hydrostatic equilibrium between the explosion coming out due to fusion and gravity pulling in. Well, as it runs low on hydrogen, the rate slows down. And so it has less outward pressure, the core is going to start collapsing. And as that core starts collapsing, the pressure or temperature right outside the core is going to start elevating. And we'll get to the condition where you can have hydrogen fusion occur outside of the core. And then the hydrogen fusion outside the core is going to go whoosh, and we have a big, grand, growing star, a giant stage. You keep throwing more helium into the core, and you will reach the point where then the helium core starts fusing to form what is helium forming in fusion. And then this is why I want to go with this. It actually forms carbon. It's called the triple alpha process because a helium nucleus is also called an alpha particle. And you have to have 3 alpha particles all come together to make the carbon. So you have to have 2 helium come to hit each other, and before they break apart in a billionth of a second, you have to have another helium hit, and then that forms a stable carbon nucleus. And so our sun will fuse helium into carbon in its core. Yes?
How's that different from the, isn't it CNO?
Okay, the CNO cycle is a hydrogen fusion cycle.
Okay.
The CNO cycle, think about it as you would in chemistry. You take chemistry, right? In chemistry, you talk about a catalyst. Something that makes a reaction go, but when the reaction is all done, you get it back. That's what's going on with the CNO. You start with a carbon absorbs a hydrogen, and you go through a process of absorbing hydrogens and progressing from a carbon to a nitrogen to an oxygen, and then the next hydrogen you absorb after that, it splits into a helium and back to carbon. It's a more efficient, you have a higher bang for your buck when you have the CNO cycle.
Then it would go back to the carbon and then to the nitrogen.
Yeah, and so the same atom can go through and facilitate many fusions. Okay, but the sun will fuse helium into carbon in its core. When it does that, it will reach a new stability. Just like the main sequence had stable hydrogen fusion in the core, we're going to have then stable helium fusion in the core and another stability. That's going to run out quickly. There's a lot less helium than hydrogen because for hydrogen you need to make 1 helium. And you have to have much higher temperature pressure, which means you have to have much more fusion going on. When the helium runs out, you will start a helium shell burning out, and sun will be done. Bigger stars, they will have other shells that burn out. So you'll have a silicon shell as the last shell, I think, that burns out. And then you form an iron core. That's how we get up to iron. All right, we will meet again if the weather's clear. I expect some of you to give me a call tonight, and we'll go out and freeze our buns and point out stuff in the star quiz. I see Clayton's little happy grin there because he's not one of those.
Oh, yeah. I already had my time.
I was so blown up last night, then we stayed in here. I was boiling, then we got there, and you could see stuff that just, I don't know, it's kind of hazy on the horizon. And part of me says, what if it's not clear now? I said, trust me. What if you shouldn't trust me?
It's supposed to be cloudy.
It's supposed to be
It's supposed
cloudy?
to be cloudy. Yeah.
You are the one who said.
Well, that's what I said
I
yesterday.
know. I know. I should blame you for faulty weather.
Wait, how cloudy? How cloudy?
Completely cloudy.
No.
This is
Well,
supposed to be
we
like
hit the little final.
Yeah, I will let you go through finals week just because I want you to have a chance
There
to
has
do
to
it.
be at least
One night. I can imagine being on Facebook. That just.
It's horrible. It's horrible.
They did a provisional on paper last night.
Oh, God.
It's horrible.
All I know is
Because we studied the one that we practiced.
Besides, you already got 30,
Change
didn't you?
the-
Yeah.
It was like